My name is Leon Barron. I'm a solutions architect with Tigera. I mainly deal with customers, some of whom I can see here, kind of going through, I suppose, architecture, design, how to get the most out of the product. Today I'm going to be talking about nftables and why you might want to consider maybe moving away from the IPVS data plane and Kube-proxy over to nftables. So what we're going to do is, a lot of this is very Kube-proxy related. So we're going to start off with just kind of refreshing ourselves with the Kube-proxy data plane options. What options do we have available to us so that we're all on the same page? Then we'll ask the question, okay, well, why would I even bother moving away from IPVS? We'll talk about IPVS, why that could be a potential alternative to IPVS. And finally, nftables, why could that be a potential alternative to IPVS? All of that is pretty much Kube-proxy based, so I'll kind of touch a little bit on Calico and how that interacts with nftables as well. And then finally, there's a lab that most likely I won't get a huge amount of time to go through. If I do, I'll do a demo, but if not, there's a QR code that you guys can look at as well, and it's a really nice one. It goes through kind of how you install the cluster, how Calico does natting and masquerading with nftables, and how Kube-proxy delivers services. Okay. Now, credit where credit is due. This is a really nice Kubernetes enhancement kind of post. I took some information from that. If you want to dive any deeper, that's the place to go. Okay. So let's start with the Kube-proxy data plane options. So before Kubernetes 1.29, we essentially had two options, right? We had iptables and we had IPVS. With iptables mode, what happens is traffic comes in from the outside or within the cluster. It's destined to a service IP address. And Kube-proxy is going to program the iptables data plane to match that destination service IP address and then shift it off to an endpoint. Okay? Now, how iptables does that is in a linear fashion, right? So if you have 10,000 services and you're trying to get to the 10,000th service, you got to go through 9,999 services to get there, okay? So it's a big O of N. As you scale your services, the latency cost increases. When iptables then wants to send that traffic to an endpoint, so this is all done in kernel, which is good, the matching and the endpoint selection. When he wants to send it to an endpoint, it's done using equal cost probability. So if you've got 4 endpoints, each one has a 25% chance to get that traffic, okay? Not round robin, equal cost probability. So that's the default mode that we had and currently have, and is generally seen as good enough, right? Battle hardened, it works well, happy days. Now the next mode that we have, and one of 2 modes before 1.29, is IPVS. The theory behind the packet matching is pretty much the same. So again, traffic is coming in destined to a Kubernetes service. Kube-proxy at this point programs IPVS as opposed to iptables. And IPVS is going to do that service matching and then shift it off to the endpoints. Now what we can say is that IPVS is more efficient than at least iptables, because when it's choosing that service, it's not doing it in a linear fashion, right? It's doing it using hash tables. So it hashes the destination address, destination service information, and then based on that hash, it's going to pick that service. So if you have 1,000, 10,000, 30,000 services, where iptables kind of scaled up with your latency, with IPVS, that should remain pretty static. Okay. Now, the other benefit to IPVS is the load balancing mechanism, whereas with iptables, you had equal cost probability. IPVS has far more advanced load balancing mechanisms, and really that's where it shines. Okay, so with IPVS, you could have round robin, least connection, weighted round robin, algorithms that you would commonly find with load balancer services. That's all in IPVS. Okay. Now, one thing to note with IPVS is that it doesn't do any packet filtering. Okay. its bread and butter is that service selection and load balancing to the endpoints. Okay. So previous to 129, there were our two options. Going into 129, if I can get this guy back. Yep, so in 129 and above, we have the nftables option. So 129 nftables was alpha, 131 it's beta, and in 133 it's expected to go into GA. Again, it's very similar, design principles. Traffic is coming in, it's hitting a service. This time, Kube-proxy is programming the nftables backend. It matches that service to the destination service to the service endpoints you've created in your cluster and then ships it off to an endpoint. Now, where nftables gets those performance wins over IP tables is that nftables, like IPVS, is not a linear search. So nftables is going to use verdict maps to hash the destination information and just go straight to that service. So again, if you have 10,000 services, whereas IP tables, you go through them all. With nftables, they're going to go straight to that service. Now, when he shifts it off to an endpoint, we're not using equal cost probability like we did with IP tables. We're also not using more advanced load balancing mechanisms that we have in IPVS. It's somewhere kind of in the middle, where we're using hashing or round robin based on random numbers. Okay. So they're the three options that we currently have if we're looking at Kube-proxy data plane. So the first question obviously is, well, okay, IP tables works, good enough. Why would I even consider moving away? Right? The first point is obvious, as I've kind of covered it a few times, is the performance and scale considerations. So performance-wise, obviously you've got the linear search, but also if you want to make an update to one service, you need to dump the entire IP tables rule set, make that update, and then push it back again, right? And Kubernetes doesn't tend to be a very static platform. There's updates happening all the time to services and endpoints. So, the bigger you get with your services, the more costly this operation is going to be. Okay. There's also compatibility constraints. What I mean by compatibility constraints is that certain features in IP tables are now considered to be kind of bad ideas, but we can't really do anything about them because there's users that are using these features, right? An example of a feature would be the ability to hit node ports via localhost, okay? Normally when traffic comes in and it's going to hit, a node port destined to 127.0.0.1, the kernel would say, no, that's a Martian packet, that shouldn't be here, and it will drop it. In IP tables mode, we want that to be allowed. So to do that, we're setting sysctl values, and it allows it to happen, but then that opens you up to certain CVEs and vulnerabilities and things like that. Maybe we don't want to maintain, but we have to because people are using them. Okay, and if we were to change it, then it would break those users. Right? And then finally, most advancements that are being developed are going into nftables. They're not going into IP tables. IP tables is quite static. And vendors like Red Hat has declared IP tables as deprecated in RHEL 9, and potentially it's going to be gone in RHEL 10. So again, I'm very much of the opinion that if it works, if it ain't broke, don't fix it. But at the same time, it's worth considering, okay, well, what does the future hold for IP tables? But we had another option, right? We have three options: IP tables, IPVS, and nftables. So what about IPVS? Why can't we make IPVS the default mode for Kube-proxy? And that's exactly the question that was raised in this GitHub issue, a kind of a discussion to see, okay, what would it take to make IPVS the default data plane mode for Kube-proxy? And it's a nice read, well worth going through. It's like a Martin Scorsese's movie. It starts off all hope and it ends in disaster. But it's worth reading through. Really what people found out was that there was kind of operational challenges. So things like, missing or disabled IPVS modules. There might not have been complete test coverage. And also there were some compatibility issues with IP tables. And that brings me to the next point. And the eagle-eyed people in the room would have seen in my IPVS slide that I had a little bit of IP tables going on down at the bottom. And the reason is because IPVS on its own doesn't actually have the ability or the functionality to create Kubernetes services. So it actually relies on IP tables to do some of that. So if we were going to move over to IPVS fully, then the bits and pieces that it needs in IP tables would have to be ported over to nftables. But at that point, why not just go to nftables, right? Really, we just be benefiting on the load balancing algorithms in IPVS. So all of that to say that there's been stagnation with the IPVS development, and like IP tables, IPVS has kind of stopped with development. Okay. Now, before I move on to nftables, I'll get this guy back again. Let's just talk quickly about how the Linux operating system has been dealing with this transition, because most modern Linux operating systems are using nftables, okay? But nftables, the nftables option in Kube-proxy and Calico is quite recent, so what's been happening in the years between there? So there's 3 modes that you can work in the Linux operating system. One is IP tables mode, and that's IP tables API commands programming the IP tables backend, or xtables. There's the nftables mode, which is nftables API commands programming the nftables backend. And then there's IP tables NFT. And what IP tables NFT is a translation layer, okay? So you've got something, an application, something that's sending IP tables API commands, but it's going to program an nftables backend. So this IP tables NFT, you can see it's in user space, and that translates those IP tables APIs to program nftables. Now both Calico and Kube-proxy heavily utilize this while we were kind of in a migration phase before we could program nftables directly. So a very useful tool, but you kind of have the best or the worst of both worlds here, because you can't use any of the I suppose the performance enhancement features in nftables because you're using the IP tables API, so you don't have access to verdict maps, and the updates are as slow as they are when you were in IP tables mode. So yes, you're programming the nftables backend, but really you're confined to the IP tables performance world. Okay. And that leads us on to nftables. So why would you consider nftables? So as I'd mentioned, there's the performance and scalability. So when we're talking about service matching, that's a big O of 1. So you're using verdict maps to hash the destination information, go straight to the services. So as this scales, and we'll see it, I think in the next slide, it scales. It stays pretty much similar depending on whether you've got 5,000 or 30,000 services. It also addresses the problem with IP tables where if you want to update or one service needs to be updated, I don't need to dump the entire rule set, make the change and put it back again. nftables, you're able to just update the deltas, whatever changed, update them and put it back again. So again, scale considerations. And we would see it as a unified framework. With IP tables, you have IP tables for IPv4 filtering, IP6 tables for IPv6 filtering, ARP tables for ARP filtering. NF tables, if you want to filter IPv4, IPv6, it's all in the one tool. Now everyone's going to be interested in performance, right? And luckily, there was some performance stats that came up in February, so I can present them to you. Before I get into it, people are going to be interested in, obviously, IP tables compared to NF tables. And there's going to be someone asking about NF tables compared to eBPF. I'm going to tell you right now, I don't have the data, okay? So you can set your expectations. Generally speaking, comparing NF tables to eBPF, they're quite different. And where they differ the most, I believe, is the access to the kernel, right? NF tables has access to the net filter hook, whereas BPF has access to TC hook, XTP hook, net filter hook, and a whole load of other hooks, right? So the odds are you could probably squeeze a little bit more performance out of BPF, but it's going to come at a cost of complexity, right? You're replacing the network stack of the Linux operating system. So, you know, this is more, I suppose, native to the operating system, right? Now, the other part of that, the conversation with eBPF, is that some of the benefits that eBPF gives would be things like, okay, it's using a hash table to match the services. Well, that's in nftables. Oh, there's a happy path or a fast path through the network stack to make it a little bit faster in eBPF. Well, with nftables, you've got flow tables that does something similar, right? So you're in and around that type of performance, but I suppose Calico is a pluggable data plane. If you want IP tables, it's there. If you want nftables, it's there. If you want eBPF, it's all there. Okay. So all of that to say, I don't have the data, but I do have the data for IP tables, and you can see it's pretty much what we would expect, right? This guy here over in this is IP tables. These are percentiles, so we can just focus on the median, but you can see with 5,000 services, it's whatever latency, but once you get to 30,000, it goes up considerably. nftables, it looks like it's scaling, but if you look at the y-axis, those times are much smaller than this. And this is the real one here where we're comparing nftables to IP tables. IP tables is going up, nftables is remaining static. So I've spent this whole time talking about Kube-proxy. How does Calico relate to this? So Calico mainly interacts with nftables for network policy. It also interacts for masquerading, so that NAT outgoing true statement. Kube-proxy is going to interact for service endpoint translation. Calico is already pretty efficient. Even in IP tables mode, those length of chains, they're really reduced by using IP sets, so when we move over to nftables, there is a bit of a performance win, but like I said, it's already pretty efficient in IP tables, but Kube-proxy is really going to benefit from this. Having said that, both need to be set to nftables, right? There's an issue there that I've got linked that kind of explains what happens when they're not both set to nftables, but that's just a rule of thumb. Set Kube-proxy to nftables, set Calico to nftables, you're good to go. And then I'm not going to have time to do the lab, but I'll have QR code in a second. But the idea is that if you want to deploy a cluster with nftables, you need to meet the requirements. So you need to have a kernel version, NFT version. You need to have Calico 329 or above, Kubernetes 129 or maybe 131, I suppose, or above. And then you're just setting the Linux data plane modes to nftables on both. And that's it. This is a lab that goes through all of that, how nftables looks in the background, chains, tables, etc. Well worth checking out. Any questions?
How's the migration?
Okay, I'm glad I tested it now. So I don't believe that we have tested the migration just yet. So what the lab is doing is deploying a new cluster, setting it at nftables. I predicted someone would probably ask this. So in a lab, I tested it, and I had a pod curling a service the whole time just to see. And sorry, the question was, what's the migration process like? So if you're already on IP tables, migrating to nftables, what's that like? In a lab, I didn't see any drops, but it's a lab, so I certainly wouldn't recommend it in production. And it looks like the recommended way is to deploy the cluster, but that's what I saw.
You do want to clean out your IP tables. Calico doesn't clean out the IP tables. I think that's something that we'd like to do for the next release.
Cool. Any other questions? Oh yeah.
Can you do this migration like per node and just like spawn up new nodes and
So the question was, can you do it per node?
Yeah.
I mean.
Just you have IP tables running in the whole
Yeah.
and like you spawn one by one and just slowly migrate to nftables so you don't have to do.
Yeah, I mean, it kind of goes back to the first question of that kind of live migration that I don't think that we've tested. I tested, it seemed okay. Doing it per node, I mean, off the top of my head, I think that it may work, but it's not tested because every node has its own, IP tables chains or nftables chains, and a decision is made at the source, right? So if it's east-west traffic, potentially, but I haven't tested it. Sean looks like he might have the answer, though.
Is it on?
Yeah.
Yep. So I think just in the first release, we haven't implemented migration. The only thing that needs to be done to implement migration is to delete all of the Calico IP tables rules that were left over. So when Calico's in nftables mode, it doesn't even look in IP tables. It assumes IP tables is not there. We just need a little special case that says, oh, do one little pass over the IP tables to delete any Calico chains. We haven't done that. So the safest way is to switch it over and then do a rolling reboot, or do a rolling upgrade of your nodes or something like that, or just deploy a new cluster in nftables mode so everything's in sync from the beginning. But it was only released in the last version of Calico. It's one of those things where we waited for the Kube-proxy to do it because Calico doesn't work with Calico nftables can't work with IP tables Kube-proxy. They were kind of waiting for us to do it, and eventually they did it. We did it as quickly as we could after that, and that was in the 3.29 release.
Cool. I'll stop there because there's other presenters to come up. But, thank you very much, guys. Any other questions, we can grab it at the end.